So what you're looking at here is called the Half-Life Decay series of, let's say, a very unstable nucleus, uranium-238. And as we know, uranium-238 undergoes alpha decay. So this graph plots the nucleon number versus the proton number, and this graph of N versus Z tells us something about the number of decays and the time frames in which these decays occur in order for an atom like uranium to become more stable. You can see that if you follow the arrows along here, that eventually this uranium nucleus over all these different time frames will find a most stable state in 206 lead. But for this to happen, it has to undergo a certain number of decays. Now we're just going to focus on the alpha and beta minus decays here, keeping in mind that the purpose of this is to reduce the binding energy per nucleon. So as the nucleus decays, the binding energy per nucleon decreases and the mass number per nucleon increases. So let's have a look at uranium-238, and we know uranium-238 undergoes alpha decay, releasing an alpha particle. Now I've highlighted this arrow here, there's my decay. An alpha particle is released, that's called alpha decay, and the daughter nucleus becomes 234 thorium. So there we have it. Now this is one disintegration or one reaction, but in reality, if we have a sample, a rock, let's say, of uranium-238, for argument's sake, if we've got a kilogram, the time it takes for half that sample, in other words, for half the uranium, half a kilogram of uranium, to transform to 234 thorium is 4.5 by 10 to the 9 years. So that's the time for half the amount of a sample to become stable. Now that's called the half-life of that particular nucleus. Now a further decay will result in greater stability, but thorium will undergo not alpha decay this time, but you can see here the beta decay. So it goes from 234 thorium to 234 protactinium. The decay is beta minus decay, and it releases the beta minus particle. Now the half-life for this is a lot shorter, of course. We've got 24 days for half of the amount of thorium to become stable protactinium. Now this pattern continues. So as we continue this pattern, we go from 234 protactinium to 234 uranium. Now here is our reaction, and again it's beta decay. You can see the half-life there is 6.7 hours. Then we have a further decay. This time it's an alpha decay, so the daughter of the previous nuclear reaction becomes the parent. It decays and it produces a more stable 230-90 thorium. Now this pattern continues and continues and continues until the uranium nucleus that we started with, the 238 uranium nucleus, becomes the most stable nucleus it can be, and that happens to be 206 lead. So the previous graph is called the decay series of an unstable nucleus, and in that example we looked at, it actually represented the decay of uranium and the alpha and beta decays it needs to go through to become the most stable state of itself that it can be, and that was lead. Now what that tells us is that every radioactive isotope, especially those that have a heavy nucleus, will undergo decay at a specific constant amount of time. We call this constant amount of time the rate of decay. And you can see in this graph here, we have the time on the x-axis, and we have the number of radioactive nuclei remaining in the sample after decay on the y-axis. So n represents the nuclei remaining, and as we said, the x-axis is the time in half-lives. Now this time will vary. As you saw in the previous example, we had times with certain decays that were very short, and we had times that were extremely long. So let's analyze this graph now and see what sense we can make out of it and what it tells us about the rate of decay. Now, the first thing we'll do is we'll consider the time 0. So when time is equal to 0, so that's when we start to measure the decay of a radioactive isotope. Say we use something like a Geiger counter. We take that time as 0, and we say that there are 1000 by 10 to the 3 nuclei that are radioactive. So n is equal to n0 time, which is the initial nuclei available in this sample. Now, what we can start to do is we can start to look for a mathematical pattern or a mathematical relationship. Now we know this is not a linear function, so it obviously with time we can see here the number of nuclei remaining decreases, but at a non-constant rate. Now, since we're talking about half-lives, we think maybe there's some type of exponential series here. So we'll call this equation, this relationship, n, which is the number of nuclei remaining, n naught, the original, times the half-life, or 1/2, to the power of 0. Now this happens to be our 0 time. Now as we know, when t equals 0, a half raised to the 0 power is just simply 1. When we repeat this pattern for t equals 1, so when we say at this point here, so that's after 1 half-life, t to the half, we have 500 nuclei, or 500 by 10 to the 3 nuclei remaining. And therefore we can write our relationship as n equals n naught, a half to the power of 1 representing the first half-life. So this is the initial time of half-life, which is 0, and this is the first half-life, and we have 500 by 10 to the 3 nuclei remaining. Let's do one more. When we take the next half-life, which is the second half-life, and we go to the graph, we see that there are 250 nuclei remaining. So keep in mind this is from data that has been collected using something like a Geiger counter, which measures the rate of decay. So when t equals 2, that's the second half-life. Our number of nuclei remaining is 250 by 10 to the 3. We put this into our relationship, so there's n naught, that's the original nuclei, times a half to the second life. So that gives us 250 by 10 to the 3 nuclei, which is what is predicted by the data in the graph. We can therefore write a generalized equation that we can use to work out how many nuclei remain after a given number n of half-lives that have passed. Now that represents the time, obviously, in half-lives. So number of nuclei remaining equals the original nuclei that were there when we started recording, times a half to the power of n, where n equals half-lives elapsed. Now of course n can be 0, the initial time, first half-life, second half-life, third half-life, etc. To summarize the equations that have been derived from the previous graph, here is our equation for finding the number of radioactive nuclei remaining in a particular sample, which is equal to the original amount when we started timing, half to the power of the number of half-lives. Now n can be calculated from the time that's elapsed, so what time is elapsed after we take a measurement, and the known or the constant half-life of a particular radioactive sample. We can write it like this: n equals t divided by t to the half, where t here represents the elapsed time. Now this time, the elapsed time, can obviously be in seconds, minutes, hours, days, months, years. So we can pick up, let's say, a rock that contains uranium, and we know that the half-life of uranium is something like 10 to the power of 5 or 6 years. Or we can pick up a sample that might be used in, let's say, chemotherapy, which might have a half-life in minutes or hours or days. And from that we can work out, knowing the half-life of a specific element in the periodic table, which is a constant, we can actually work out that n, which represents the number of half-lives that have passed, can be determined, let's say, as a whole number or a decimal value. We've used the term rate of decay because, as we can see, as time progresses in number of half-lives, the decay rate is actually decreasing. So if we take a tangent at any one of these points and work out the gradient, that represents the rate of change of the number of nuclei in the sample that are radioactive, obviously over a time. So rate of change of number of nuclei divided by time. We call that the activity rate. That's R. So the rate of decay is defined as R. The delta n on delta t represents the change in the number of nuclei over the changing time, or decays per unit time. Now the standard international unit is the becquerel, and the becquerel represents 1 decay per second, so it's measured per second. Now of course we can have decay rates that are in the years or minutes or days. We always need to convert them back to the standard international unit, which is decays per second, which really just represents the number of disintegrations or the number of decays or transmutations occurring per second. So we said the standard international unit is the becquerel, and what does this rate of decay actually mean? Well, if we were to take a point on the graph and draw a tangent at that point, and then we apply our gradient of that line, delta n, so this is your change in the number of nuclei remaining over the change in time in half-lives, then what we get is a gradient of delta n on delta t, which you can see represents the rate of decay. And as was mentioned earlier, as the number of half-lives passes, so as time progresses in this decay, the rate increases, because the slope, if you were to take a point at any part of the graph and draw a tangent to it, you'd find the rate of change of the number of nuclei that are still radioactive is a function of time. Let's now try and put this theoretical understanding into a practical application, problem-solving context. This was a fairly famous case where a shroud, the Shroud of Turin, where it was assumed that the cloth that covered Jesus, that should have been about 2,000 years old, was actually, this particular shroud was that of Jesus. And this is an X-ray image of it, so they had to do a carbon dating of this shroud. Obviously the blood left behind would have traces of 14 carbon in it, which is a radioactive isotope. So if we were to consider the decay rate, we can actually work backwards and work out how many years had passed or time had elapsed. So let's try and solve this using the equations that we've just uncovered. So we're told the half-life of 14 carbon, which is a radioactive isotope of carbon, is 5,730 years. So what that means is that one half-life would represent 5,730 years. So T half is a constant. We're told that we need to find, so it says calculate the age of the shroud, so we need to find the time elapsed. And of course we can use our equations representing our relationships. Here we have n equals n naught, half to the power of n, where n represents the number of half-lives that elapsed. This is the time elapsed, and this is the constant value of one half-life. Now, we're told that the amount of 14 carbon found in it from analysis, so if we take a sample of the blood here, is 92%. So what that means is the amount that was left at death, which was the starting point of the Decay Series, was n, and this is the amount that's remaining. So that ratio, we're told, is 92%. The amount of 14 carbon found was 92% of that in living tissue. So at the point of death, it no longer is living tissue. So that ratio is 92%. We'll convert that to a decimal, which is 0.92. Then we can put the values into our equation. So we know n over n naught is 0.92, and we can find the time elapsed using this equation here. We know that that's the unknown, that's what we need to find the time elapsed, and we know the value of the half-life of carbon 14. So we want to find n. Now here is where we need to use a mathematical equation that has to do with indices. So a to the power of b equals c. If a to the power of b equals c, then that's equivalent to the log to the base a of c equals b. So we can apply that here. We've got a half to the power of n equals 0.92. We can write this as 2 to the negative n, because 1 over 2 is 2 to the negative 1. 2 to the negative 1 times n is 2 to the negative n. Now, matching our equation with the mathematical identity, let's start by looking for a. So we've got a is equivalent to this 2 here, and in our log equation there's my a, and so therefore this becomes log to the base of 2. Moving on to the indice or the exponent b. So b is equivalent to this negative n. In our logarithmic equation, that becomes b, which is this negative n here, and then we have equals c. This c here is 0.92, and in our logarithmic equation that becomes 0.92 in brackets. And if we now put that into our calculator using the log base 2 function of the calculator, it will give us an answer for the number of half-lives that have passed in the decay of this particular sample. Now that gives us 0.12 half-lives. We can convert that to years, because we know that 0.12 of a half-life is what we've got in our answer, and we know there's 5,730 years per one half-life. That's our conversion factor that we get from our constant, which is the half-life of carbon-14. And by doing that, we work out that in reality 689 years have passed since this person that was meant to represent Christ died, and obviously that does not match what history tells us. So that's how we would use our relationships to actually solve real life problems. Let's have a look at another type of problem this time using the same relationships. We're told that uranium has a half-life of 4.46 by 10 to the 9 years. So we know that's constant, that's like clockwork. And we're asked to find out how much of that radioactive isotope that may be found in a particular sample would be present in a sample that was 2.5 by 10 to the 9 years old. So what is the value of N after 2.5 by 10 to the 9 years have elapsed? So that's our TE. We're also given this information that there was 2 grams present initially in this sample, and using our relationships, our equations, we simply put the values into the equations. So the time elapsed 2.5 by 10 to the 9 years. The half-life of a uranium-238, 4.46 by 10 to the 9, and we solve that and we get N equals 0.56. Therefore the number of nuclei remaining, which is our unknown, is the original amount that we were told was present times a half to the power of 0.56. So again, a value we place into our calculator, and we get that there's 1.36 grams of that original 2 grams remains in this radioactive sample. Let's have a look at another example of using these decay equations. Here we've got the half-life of thorium-234 is 24 days, so we can write down our T half equals 24 days. If we had 100 grams at the beginning, so N naught equals 100 grams, how many grams would be left? So that becomes our unknown. How many grams would be left after 96 days have elapsed? Again, we write our equations that we need to use, and we substitute the values in. We have 4 half-lives, so if this is the elapsed time, 96 days, the half-life is 24 days. That represents 4 half-lives. And putting those values into our equation, it becomes N equals 100 grams times a half to the power of 4, giving us 6.25 grams. So 6.25 grams is left in this radioactive sample that contains thorium-234 after 96 days. Here is a slightly more challenging problem. Let's go through it and analyze it, and let's try and solve it. So this time we've got a chemist determines that a sample of petrified wood has a carbon-14 decay rate. So we're told now that the rate is 6 counts per minute for every gram. And the question asks us to find the age of the piece of wood in years, given the decay rate of carbon in fresh wood today is that many counts per minute, 13.6 per gram, and the half-life of the carbon is 5,730 years. So the first thing that we notice is that we're not given, in this particular case, the number of nuclei, but we're rather given the rate at which the nuclei decay. If you can recall from previous discussion we have, the rate is really the gradient at any particular point. 13.6 counts per minute per gram. So the final counts per minute is 6 in this particular case. We're given that in the information. So fresh wood is 13 counts per minute. That represents the rate at the time of measurement, and once we pick up the petrified sample of wood, we measure its count rate. That's assuming after it's died, that the count now is 6 counts per minute per gram. Now we've got to identify or recognize that if our relationship for the number of nuclei remaining is n equals n naught half to the power of n, then it's the same relationship, but instead of talking about number of nuclei, we're talking of rate at which the nuclei are decaying. So R final, what's the rate at the end? If the original rate, that is the rate of carbon 14 in living things, is 13.6 counts per minute per gram. And again, we can find n using elapsed time over half-life. So the ratio of the final counts to the initial count is RF on RO, which is a half to the n, giving us 6 on 13.6 equals 0.44. So we're given these values, and that of course equals a half to the power of n. So we can rewrite this equation here as 0.5 to the n, that's that one there, equals 0.44. And using our identity for indices and logarithms, we can actually solve the problem. So we've got A is 0.5, B is n, which is what we want to find, and we want to find the time elapsed before we can find the age of the wood in years, and we've got 0.44 is equivalent to C. So putting that into our logarithm equation, we get log 0.5 equals 0.44, which is equal to n. So n is equal to 1.2 decays. To convert this to age in years, we simply use our half-life conversion factor for carbon 14, and that gives us n equals 6,765 years. So what that tells us is that the rate of decay in fresh wood, for example in living plants, is 13.6 counts per minute per gram. So if we were to take a Geiger counter and put it on a tree, that's what we'd get. Once the tree dies, the decay rate slows down over the years. Obviously, if the dead wood had a count of 6 counts per minute per gram, then that must mean 6,765 years have passed.